So in step 3 we talk about J3 pi. So here there is a problem because J3 pi is not evaluated at some particular time point tk minus 1, it is at some eta k. Okay, so and also here we do not have mt difference or a difference, we have xtk minus xtk minus 1 whole square. So a lot of things has to be done here, okay, to make it streamlined and straightforward so that we can analyze. So J3 pi is therefore rewritten as sum of 3 different objects, J4 plus J5 plus J6. What is J4? J4 is that, so there whatever I had xk, so writing only a, okay, instead of x I am writing a, okay, atk minus 1 whole square. So here square of this thing was there, here a square of this thing. However, we should have also cross terms, so a and m together, so the 2 times of, because xtk minus xtk minus 1 whole square would be this square plus 2 times this square plus this square. So we are writing these 3 terms therefore, okay, eta k eta k eta k everywhere. So J4, J5 and J6. Later we would also approximate J6 by replacing eta k by tk minus 1. Okay, so for the time being let us consider J4 and J5. As A is a bounded variation, for J4 and J5 we have a nice bound. Why is it so? Because here f double prime is bounded function, and atk minus 1. So this square I can write down as a product of this with this. Okay. Now in this product, one term I can take supremum of all possible tk, and when I take supremum of all possible tk, that particular term, okay, becomes independent of k and can come out of the integration, and the remaining term, okay, that I am going to take as a toleration. So we are doing that. So this maximum of atk minus 1 mod of that we are taking out of that summation, and then this also is bounded, so that also I am taking out of the summation, and then what remains is mod of atk minus 1, then the summation that would give the bounded variation of A. So that bounded total variation of A is obtained here. Okay, and as we have seen for here also, if we take maximum over all these things, okay, the difference of martingale increments of the martingales over all possible k, of course after taking modulus sign, then that maximum is independent of k, that can come out of the summation, and what remains there also has modulus, and here this is also bounded, this also the going to come out, that the maximum of that, the upper bound comes out of the integration summation, and we are also going to get the total variation. Now we see that this does not depend on the choice of partition, correct? This is independent of partition, but this depends on the partition. Now if partition mesh size goes to 0, what happens? Okay, so these are continuous functions, okay, and then as mesh size is going to 0, so here we have taken, say, this partition 0 to t time, okay, closed interval 0 to t, and then the continuous function is uniformly continuous, and then when we are taking this difference goes to 0, the whole thing goes to 0, so this maximum goes to 0. Okay, this goes to 0 as norm pi goes to 0. So we are going to obtain this, that J4 plus J5, okay, that goes to 0 in L1 also. I mean, this is almost sure convergence, but from there we are going to L1, because that boundedness we are going to use, the dominant convergence theorem we can use to obtain the L1 convergence also. Now next we discuss what would be about J star 6. Okay, so J star 6 is okay, so J6 pi, actually I talked about J4 pi and J5 pi, but J6 pi is further approximated by J star 6 pi. Okay, J star 6 is nothing but the thing where this eta k is replaced by xtk minus 1, and summation is there. Here the summation is also from k is equal to 1 to m. Okay, now we consider this difference, and in this difference, Okay, here we are going to get eta k, and here we are going to xtk minus 1. Okay, so the maximum of that, if that maximum difference I take out of the summation, I would get one upper bound, and then remaining term square of this is nothing but the quadratic variation v2t pi. Okay, and we have seen already a result earlier that if we have this v2 pi, that converges to the quadratic variation of m, correct? So this is defined earlier. So here we are going to also use another result which you have not quoted before, but this is giving, I mean, instead of directly using this convergence, okay, we are also using another, estimate that this expectation of this random variable, okay, is less than or equals to 48 times k to the 4. Okay, is a very particular type of, upper bound. One can get the details of the derivation of this upper bound from the book of Karadzic and Schiff. Okay, the book what I am following for this part. Okay, so where mod of xt is less than or equal to capital K. Okay, so that is true for our case. Then the way we have defined, I mean whatever the k we first, if this is less than or equals to mod k, k, then this would be less than or equals to 48 times k to the 4. From here, if we take expectation both sides, okay, so then expectation of this, we can obtain that this is less than or equal to square root of expectation of maximum of f double prime eta k minus f double prime xtk minus 1, this whole square, okay, maximum of all these, and square root of 48 times instead of k to the 4, I have k square here. Okay, so now what is the behavior of the right hand side? So this is fixed, but this as k as per mesh size goes to 0, then eta k comes closer and closer to xtk minus 1. Okay, and then this maximum of all these that also goes to 0, as we have explained earlier. So but this is actually bounded function, so inside this thing converges to 0, so after event of taking expectation, that also goes to 0. Okay, using dominant convergence theorem, so we get that this is j star 6 is approximating j 6 pi, in the sense that the difference goes to 0 in L1. So from here, how can we get the j3 minus j6 star pi also goes to 0? Thing is that j3 is j4 plus j5 plus j6. So this total sum, the modulus goes to 0, and j6 minus j star 6 plus j star 6, I can add and subtract, and that difference goes to 0. So j star 6 remains here, and this j star 6, if I put this side, then I get j3 minus j star 6. Okay, so this right hand side goes to 0, left hand side also goes to 0. So what we get is that expectation of this goes to 0. Okay, you remember earlier all this L1 convergence we obtained. Okay, so all other in the same notion, this is important, correct? I mean, so because of this L1 convergence here, we get this goes to 0. Okay, so next what we obtain, we see that we would like to further take another sum j7 pi. Okay, so in the j7 pi, what we have like discretization of the Riemann-Stieltjes type of integration with respect to the quadratic variation of m. Okay, so we have to relate this j7 with this j3, otherwise we are not yet done, because remember that when we have stated this here, integration was with respect to quadratic variation of m. Okay, till now j star 6, which is approximating j3, is like mtk minus 1 whole square. Okay, so this integration. Okay, but this is not in the form of integration, correct? Because this is like square of an increment. So this we can put only in terms of Stieltjes integral when it is like is an increment of some process. Okay, so here we take its increment of the quadratic variation process j7. Since m and mt square minus quadratic variation mt both are martingales, there is a definition of quadratic variation, both are martingales. So mt minus ms this time, and then difference of this thing, that is mt. If I put bracket, then I would mt minus ms. Okay, but if I open the bracket, then I will get minus mt plus ms. Okay, so this given fs is 0, correct, because this is martingale. Since this is martingale, so its difference in, so we now consider j6, j star 6 and j7. Okay, and we are taking L2 norm here. We are going to show L2 norm goes to 0 first, and then we are going to get L1 norm convergence also. So now j star 6 pi minus j7 pi, this mod square. Okay, so the L2 norm we are taking, expectation of summation. So now we are just writing down the definition. Okay, just exactly. So j star pi is like this, xk minus 1 m this whole square, and for j7 we are getting exactly this thing, but now integrator term is like this. Okay, I think some bracket is missing here, so here there should be a bracket here and a bracket here. Okay, so is equal to expectation of summation 1 is equal to 1 to m. Okay, then we are writing, okay, so this is f double prime square times the mtk minus whole square. Okay, minus this, I mean the whole thing, whatever I had, this whole square. How did you get it? Because we know that for cross terms their expectation is 0 because of the martingale property of this thing. Okay, and basically we are going to use this thing for here. Okay, then when we have obtained this, square of the sum is sum of the squares. Okay, so then this boundedness property of f double prime we are going to use to obtain the f double prime square. So we are going to estimate this by the upper bound of this, and that is independent of k, that we take out of the summation, and then expectation of summation 1 to m, then inside term that we have difference and then whole square. So if I write down fully, so this to the power of 4 appears, and then this to the power of square also appears. Okay, so this is properly written in the brackets, and the cross terms, etc. Okay, so then there also we are going to again use the earlier thing to remove that. Okay, so we have this upper limit. Now here what is this? This is like quadruple variation. Okay, like to the power 4 vt to the 4 pi. Okay, expression of that, plus and then this here I have a square, so I can think that okay, two terms, I mean this term is multiplied twice. For one term we are going to take the supreme, replace that by supreme of all possible k, that would be independent. Okay, that I take out, so that I call the maximum of increment of quadratic variation of m, and the remaining term would be just telescopic sum. Why is it so? Because mtk is increasing, correct, increasing process. So when I take out of this maximum, I do not need to change the sign. Okay, so then this delta mtk, okay, and then remaining term is like this sum, we are going to get mt minus m0. So we have seen that j star 6 and j7, the difference between j star and j7 square and an expectation, this is nothing but the square of the L2 norm of j star 6 and j7. We have seen that as a norm of pi, the partition goes to 0, the difference, I mean the L2 norms difference, okay, that also goes to 0 of j star 6 and j7. From here we can conclude that okay, j star 6 and j7 both have same L2 limit. Okay, they have the same L2 limit. Here we have seen that okay, this norm is less than or equals to this finite number, and then this part where maximum delta m quadratic variation mtk, that goes to 0 as the partition mesh size goes to 0 due to the continuity of the martingale. Next, and this, since we know that L2 convergence implies L1 convergence, so we can state that, okay, J star 6 and J7, okay, so this different expectation of modulus of this difference goes to 0. Okay, so from here what did we conclude? We conclude that this J3 and J7 would have the same L1 limit. Okay, where does J7 converge? J7 converges to 0 to t double derivative of f, and the integrate the double derivative of f at xs with respect to quadratic variation of m from 0 to t. So that would be the limit of J7. Why is it so? Because the construction of J7 is constructed this way, where this is the integrand tk minus 1 at the interval tk minus 1 tk. So it is taking the value at the left point, and then the integrator, the increment of the integrator is here. Okay, so that is the reason that this is like nothing but Riemann-Stieltjes integration sense. Okay, so J3 converges to this integration in L1, and this is the integration what we want in the expression of Ito's formula. So now what do? We have obtained only L1 convergences. Actually, at some places we have obtained almost sure convergence, for example for J1 and J2, correct. So I mean here for J1 we have obtained that almost sure convergence, correct, but then weaker form is L1 convergence. Okay, however, we actually want to have one single settings for each and every terms convergence, because sometimes we did not have almost sure convergence, we have only in the sense of some mean or square mean L1 L2. So we used the boundedness of the integrands and integrators, and using that we got all terms convergence in terms of L1 in the sense of L1 convergence. And then if a sequence of measurable functions converges in L1 sense, okay, then that would also imply that it converges almost in measure. Okay, so here measure is probability, so that would imply that the convergence is in probability. Okay, however, if a sequence of measurable function converges to say for example 0 in probability, okay, then there is a subsequence which converges almost surely. Okay, so here what is the sequence we are getting? We are getting sequence due to the partitions. Okay, the final and final partition, we are getting the newer sequence. Okay, newer terms of the sequence. So if we talk about a subsequence, then you have to take a subsequence of the partition sequence. Okay, as that partition mesh size goes to 0. So we take this subsequence of the partitions. Right. So initially I have not fixed any particular sequence of partitions. Okay, but here if we have such convergence for some sequence of partitions in L1, then of course for that particular sequence there is a subsequence, we call it this pi superscript m. Okay, so that converges to 0 as m tends to infinity, and on along this subsequence of partitions J1, J2, J3 all converges to the respective limits. Okay, so this is actually the sequence m, but mk is the subsequence. Along this subsequence mk, that would converge almost surely. So let us write down that things whatever we have obtained. So these three convergence, okay, 1, 2, 3. So limit n tends to actually here there is a typo, I should have written k, correct. Limit k tends to infinity J1 pi mk. Okay, so that limit is integration 0 to f prime xs das. Okay, and limit n tends to infinity. Actually here for these two things one could have taken the subsequent I mean the sequence itself as a subsequence, correct, because we already had almost sure convergence along that pi. Okay, however, we wanted to talk everything in the single setting, so we are considering this, and limit k tends to infinity J3 pi mk, that is equal to integration 0 to t double derivative of f xs and integrated with respect to the quadratic variation of m. Okay, so t is here fixed, okay, and you remember that the stopping time what you have introduced, that also we have fixed, we have not changed the stopping times here. So thus passing to the limit in star. So what is star? So it was in earlier few slides earlier, so I have written down again. So here this f of xt minus f of x0, the increment of this function of the stochastic process, that is written as the as the telescopic sum, and that is written as these three terms. So now at this place, if we take limit, in which sense? Now almost sure sense, correct? And then what are the sequence? Instead of pi, I am going to take pi mk. Along the subsequence, we take the limit, okay? Then we know the right hand side converges. So let me write down that. So where it converges? So j1 pi would converge to this term, and j2 pi would converge to this term, and j3 half j3 pi would converge to half of these things, okay? These things just obtained newly. And then f of xt minus f of x0 is like that, okay. Now here I am going back to the earlier notation, because here I mean because as I have mentioned that, okay, I have taken only the localized version of the process and then pretended, okay, that is my original process. Now when for that we have obtained this Ito's formula for this localized version of the process. So then we go back to the earlier version. Now this x is the original process, okay, original semi-martingale, and then what we have obtained actually in terms of original semi-martingale, only this thing, that, okay. So where it is only the localized version of the original semi-martingale, okay. F of xt n is equal to f of x0 plus integration 0 to t f prime xs dms plus 0 to t f prime xs das plus half integration 0 to t double derivative of f xs and integration with respect to the quadratic variation of m superscript n. Okay, so now the right hand side, let us recall the definition of the stopped semi martingale. There we just stopped at time tl, okay, tn, and then onward it was that exactly the same value, it did not, it was just constant there. So when my s is between 0 to t, okay, and if tn is more than small t, then this integrand and integrator everything is as same as the original one. However, if t capital Tn is smaller than small t, then only you have that problem that, okay, sometime it stops and it deviates from the original given semi martingale. So this therefore this whole integration is exactly nothing but 0 to t minimum Tn of f prime xs dms, okay. So now each term is now rewritten in this way. So right hand side is nothing but the integration of the original process with respect to the martingales. Only thing is that the upper limit is instead of time, you have time and minimum with the stopping time Tn. For each and every n you have this equality, and here we have obtained this equality. This equality is true almost surely with probability 1, okay, for when small t is fixed, and this is true for probability 1 for each and every n. Okay. Now we know if you fix omega and we vary n tends to infinity, the Tn would cross every finite time and it would go to infinity with probability 1, correct. For every omega we are going to see, every omega means with probability 1, okay. Almost every omega we are going to see that Tn would go to infinity. So if we now let n tends to infinity, okay, here on this right hand side, this small t minimum capital Tn would become small t only, okay, because capital Tn would become larger than t after a finite n onward. So that would take place at each and every term on the right hand side. So right hand side we are going to get exactly this thing as n tends to infinity, and left hand side would also be, since right hand side converges almost surely, left hand side would also converge to almost surely, and we know that, okay, that f is a continuous function, and if xtn converges to xt we know, and therefore this also converges here. Okay, so we obtain this final equation, which is not yet exactly the Ito's formula, but it looks like Ito's formula, correct. It is true for all t. Okay, what is the difference? Okay, what is the gap now? That we have obtained for each and every, after fixing every t, we have obtained this with probability 1. Okay, but Ito's formula says that that left hand side as a process and right hand side another process. These two processes are equal, okay, are indistinguishable with probability 1. Okay. So, here what we have obtained is just a modification. We have obtained the left hand side is a process, right hand side another process, and they are modification to each other, because they are equal with probability 1 for each and every t. But we need to show that for all t they are equal, that the probability of that is 1. However, since both the sides are continuous, okay, so since both sides are continuous processes, so modifications are therefore indistinguishable. Okay. So, here since they are continuous, they are indistinguishable. So, we know that, okay, this that is a proof of the Ito's formula. So, Ito's formula is complete here.